Let's talk scale because atoms and molecules, they're mind-blowingly small. Take a hydrogen atom. It weighs about 1.66 times 10 raised to the power minus 24 grams. Clearly, you can't place that on a regular lab balance. So how do chemists deal with this? They came up with brilliant shortcuts, a way to measure the mass of the tiniest particles using logical, relative values. And that's where the concepts of atomic mass and molecular mass come in, helping us measure the invisible with precision. So, how do we assign a mass to something as tiny as an atom? Chemists use a smart comparison. The atomic mass of an element is the mass of one atom, measured relative to 1/12 the mass of a carbon-12 atom. This unit is called the atomic mass unit, or U, also known as a mole. That means one atomic mass unit is equal to 1/12 the mass of a carbon-12 atom, which is approximately 1.66056 times 10 raised to the power minus 24 grams. Let's see some examples. Hydrogen, 1.008 atomic mass units. Oxygen, 16.00 atomic mass units. These aren't actual weights in grams, they're relative masses that let us compare atoms easily. Here's something fascinating. Most elements exist as a mix of isotopes. Isotopes are atoms of the same element with the same number of protons, but a different number of neutrons. So, instead of using a single atomic mass, chemists use the average atomic mass based on the natural abundance of each isotope. Take chlorine, for example, 75.77% of chlorine atoms are Cl35, 34.9689 AMUs, 24.23% are Cl37, 36.9659 AMU. To calculate the average atomic mass, we multiply 0.7577 by 34.9689 and 0.2423 by 36.9659. Then we add both results. The final value comes out to 35.453 atomic mass units. That's why atomic masses on the periodic table aren't whole numbers, they reflect these weighted averages. So, how do we find the mass of a molecule? We simply add up the atomic masses of all the atoms it contains. This is called the molecular mass, and it applies to substances that exist as discrete molecules like water or methane. Let's take water, H2O. 2 hydrogen atoms give us 2 multiplied by 1.008 atomic mass units, which equals 2.016. One oxygen atom contributes 16.00 atomic mass units. Adding them together, 2.016 plus 16 equals 18.016 atomic mass units. Now, let's take methane, CH4. One carbon atom contributes 12.01 atomic mass units. 4 hydrogen atoms give us 4 multiplied by 1.008, which equals 4.032 atomic mass units. Adding them together, 12.01 plus 4.032 equals 16.04 atomic mass units. It's that simple. Just add the atomic masses of the atoms in the molecule. Let's put our knowledge to work with some quick examples. First up is glucose with the chemical formula CSIX-H12O6. To calculate its molecular mass, 6 carbon atoms give us 6 multiplied by 12.01, which equals 72.06. 12 hydrogen atoms give us 12 multiplied by 1.008, which equals 12.096. 6 oxygen atoms give us 6 multiplied by 16.00, which equals 96.00. Now, adding them together, 72.06 plus 12.096 plus 96 equals 180.156 atomic mass units. Now let's try ammonia which has the formula NH3. One nitrogen atom contributes 14.01. 3 hydrogen atoms give us 3 multiplied by 1.008, which equals 3.024. Adding these together, 14.01 plus 3.024 equals 17.034 atomic mass units. Knowing molecular masses helps us predict mass-to-mole relationships and calculate how much of each substance is involved in a chemical reaction. Asterisk asterisk. But here's a question: what about compounds like sodium chloride NaCl? They don't exist as molecules, but as vast crystal lattices made of alternating ions. That's why we use something called formula mass, the sum of atomic masses of the ions in a single formula unit. Take NaCl, the sodium ion, written as Na+, has a mass of 23.00 atomic mass units. The chloride ion, written as Cl-, has a mass of 35.45 atomic mass units. So, the formula mass of sodium chloride is calculated by adding 23.00 and 35.45, which gives us a total of 58.45 atomic mass units. Let's simplify. Atomic mass is used for individual atoms. Molecular mass is used for molecules like hydrogen oxide or carbon dioxide. Formula mass is used for ionic compounds like sodium chloride or magnesium oxide. Each type of mass helps us measure and compare the tiniest building blocks of matter accurately and effectively. Let's quickly recap what we've covered. Atomic mass compares individual atoms to carbon-12. Average atomic mass accounts for naturally occurring isotopes. Molecular mass is the sum of atomic masses in a molecule. Formula mass is the total mass of ions in an ionic formula unit. Understanding these concepts helps us bridge the invisible atomic world with real, measurable quantities in the lab. And now, it's time to level up. In the next lesson, we dive into the mole concept, the ultimate counting tool in chemistry.